Okay, so now um, with these approximations, I want to show you a generic one-dimensional finite volume method that how you can approach this problem and use this method in reality. And of course, this method is very strong for complex geometries, especially when you have three-dimensional complex geometry, like say you have a train here and then some inhomogeneity, and then you want to kind of uh, solve for a transport equation or whatever in this domain. And using this finite volume method can be very effective for this kind of complex geometries. So let me get started with introducing a generic one-dimensional finite volume method. So in general, in finite volume method, we would like to represent everything in terms of cell averaged quantities. If you remember, in finite difference method, it was mostly nodal values, right? It was nodal values. But here it's mostly cell average quantities, like in the integral form. Okay. So the first thing that we want to do, the first step is step 1 is grid generation. When you want to deal with these kind of problems, especially finite volume method, we want to first have a grid generation, okay, with fixed CVs. And this is mostly done by some software. Kind of handle this. So usually by software. So let me show an example, a one-dimensional example here. Say we have this here. Let me do it here. So this is J, and then we have one here, the other nodes. These are the cell center. These are the centers of the cell, and this is going to be the cell that we have is this. This is going to be the cell we are considering, or control volume. This is just one dimensional. Just note, we can have two dimensions. So this is J, this is cell J plus 1, this is J plus 2, this is j minus 1, and this is j minus 2. Okay? And this is the right side of the cell, and this is the left side of the cell. This is the right side of this cell, and this is the left side of the cell. So let me make it clearer. So this is the control volume that we have, and let me show this. This is delta x here, and this is gonna be our control volume, or CV, and this is now j plus 1/2, and this is j minus 1/2. Okay, so this is our nomenclature here. So this is a grid generation. It is very simple for a one-dimensional problem here, but say if you have 3 dimensions, and then this, for example, if this is your domain, let me draw it. And then somewhere in the middle you have discontinuity, and so this is going to be harder task there, because you don't want to solve anything within that. So you have to, if you want to do the grid generation, it's going to be harder. So you might need to do something like this. And then this is a 3D, this is going to be a 3D grid, right? So you have to do it at the other side as well. So your grids will look like differently when you try to do them, okay? So a grid generation is a very important problem in general in numerics. And this becomes more important when you have complex geometries and you want to solve more complicated shapes. Like, say you want to solve for a flow around an airplane, for example. So it has like 2 wings here, and so this is gonna be more challenging, right? Say it has like 2 wings. So, for example, you need to look at, if you want to generate grids on this plane, this is going to be much more challenging. And so, for example, near the boundaries, they usually make it finer when you have these transitional regions. So this is a very important topic, but for the sake of this course, I just want to give you a very simple example. This is a one-dimensional finite volume method, okay? So this is the first step. You generate a grid either with a software or yourself. You write it yourself. For a one-dimensional one, this can be a representation of that. And then step 2, we discretize generic integral equations on CVs, on the control volumes. Okay, we discretize generic integral equations on CVs. For example, this is a general equation, V d phi bar over dt plus the integral over the surface of f phi. These are the fluxes, f phi dot n dA equals to the source term, s phi. Okay, so as you see here, it has some volume integrals, this equation, and some surface integrals that we need to discretize them. So let's first look at the volume integrals. So phi j at time t. I want to see phi j at time t. Let me do it a little bit here so you can see that graph as well. Phi j at time t can be evaluated as 1 over volume, the integral over volume of rho phi dv, which is going to be 1 over, what is v here? What is the volume of this control volume here? It is just delta x, right? If you had 3 dimensions, it could be delta x, delta y, delta z, but here we have 1 dimension, so the volume is going to be 1 over delta x. And then the integral over the volume here is going to be the integral from x j minus 1/2 to x j plus 1/2, right? For this CV, from here to here. Of phi x and t dx. We can assume rho is 1. Okay. So this is going to be the discretized phi. And then let's look at S, which is this term, S phi, another volume integral. So Sj at t is defined as the integral over volume of S phi j dv, which is gonna be integral over volume, so it's xj minus 1 to xj plus 1/2. So xj minus 1/2 to xj plus 1/2 of S phi x and t and dx. Okay. So these are volume integrals. And then the remaining one is this term, which is a surface integral. So let's evaluate that. The integral over the surface of f phi that n dA equals to, it equals to what? It equals to the flux. If we say we have the flux here, a flux that goes here minus the flux that goes from here, right? So it's gonna show how much flux in total we have inside this control volume. So I'm gonna name this f j plus 1/2, and this one f j minus 1/2. Okay. So this can be written as f j plus 1/2, the flux that is outgoing at j minus plus 1/2 point, minus the flux that is coming in at fj minus 1/2. Okay, so this is a surface integral. So using this, the discretized equation becomes so I have this term here. I'm just gonna substitute it here. I'm gonna have d delta x phi bar j over dt, and I have a v here, right? I bring it inside. plus fj the fluxes 1/2 minus fj minus 1/2 equals to the source term, which is integral on xj minus 1/2 xj plus 1/2 s phi xt dx. Okay, so this is the discretized equation, okay, for a general form. So let's look at a simpler form. So let's see how it looks like. So consider a simpler, so this is a very generic equation that for most of the transport equation it holds. So consider a simpler form, which is linear convection equation. For this equation, partial phi x and t, or partial t plus c partial phi xt over x partial x equals to 0. So we have no source or sink term here. It is 0. And the fluxes we have is a little bit simpler. The c is constant here, the diffusion coefficient. So for this one, the generic discretized equation becomes d delta x phi bar j over dt plus fj plus 1/2 minus fj minus 1/2 equals to 0. We don't have any source term or sink term, right? So now I want to calculate the surface and volume integrals for this generic discretized equation. So let me write it this way: compute surface volume integrals as function of phi within CV. Okay, as I said, we want to represent everything in terms of the cell averaged quantities in finite volume method. Okay, so this is the first step. So we have to evaluate all the surface and volume integrals here in terms of cell average quantities. Okay, so first we are going to use piecewise constant approximation. And in that approximation, I'm going to say phi x, I'm going to assume phi x equals to the cell average value phi bar j for x between j minus 1/2 and j plus 1/2. Okay. This is the first piecewise constant approximation. I'm just gonna assume that phi x that might vary within this, right? It can be up and down. I'm just gonna assume that, for example, it might vary here. I'm just gonna assume it's like the average value of that. So if you have like, this is the phi x, let me see if this is phi x. I'm just gonna assume it is the average of that. Okay. Then fluxes in terms of cell average values. So let's evaluate the fluxes. So we have these, let me show these cells here. So this is J, this is point J plus 1, this is J minus 1, this is J plus 1/2, this is J minus 1/2, this is the right side, this is the left side, right side, and left side. So the problem here is, for fluxes, you can evaluate them based on the flux on the right hand side of this cell or the left hand side of this cell. Okay, and let me show what I mean by that. For example, here I can say fj plus 1/2 r is f for phi j plus 1/2 evaluated at phi j plus 1/2 at right. And then, because this is going to be located here, right, somewhere around here, so it is within the next cell, within this cell, right? So when it is within that cell, what does that mean? Here we have made an approximation, so let me show it here. We said that we can assume that phi here, anywhere in this cell, equals to the phi bar, like phi x here, equals to phi bar j plus 1/2 plus 1, right? This is the assumption we made here. So this means if I want to evaluate flux at phi j plus 1/2 at right, this is going to be what? This is going to be phi bar j plus 1. And the flux here is nothing other than c phi. So it's going to be c phi bar j plus 1. Right? Because this is the integral I have. F phi dot n dA equals to this term, and this is going to be the flux in the integral form. It's going to be c phi. Okay? And c phi j plus, so this is going to be c phi bar j plus 1/2. But on the other hand, if I want to evaluate it at the left, So fj plus 1/2 at the left side of this boundary is gonna be f phi j plus 1/2 at the left, and this means I am somewhere here. So if I'm here, what does that mean? This means that I am in this cell. So the phi j plus 1/2 left equals to phi bar j from here, right? So this is going to give me a different result. So it's going to give me c phi bar j. So depending if you calculate it from the right side or left side, it can give you two different results. And a similar thing for here. So fj minus 1/2 left is gonna give me f phi jy minus half left, which is gonna give me c phi bar j minus 1 because I am here in this cell. And the right one is going to give me fj minus 1/2 right equals to f phi j minus 1/2 right, which is going to give me c phi bar j. So you see we have some flux discontinuity here for the flux terms. If we want to put it here in this form, we have discontinuity depending on whether we are choosing the right one or the left one. Okay, so to resolve this discontinuity, we use this method. We simply average them out. So let's see. So flux discontinuity can be resolved using a second order approximation. And that is for f j minus 1/2, I can say this equals to the average of them. This is going to be a second order approximation if you just take the average of that. So fj plus 1/2, minus 1/2 at left plus fj minus 1/2 at right, evaluated at right, over 2, which is going to be what? Which is going to be c phi bar j minus 1 plus c phi bar j over 2. And the flux for the right one, j plus 1/2, is going to be fj plus 1/2 left plus fj plus 1/2 right over 2, which is going to be c phi bar j plus c phi bar j plus 1 over 2. Okay, so this is the flux discontinuity. We can resolve it by that, and then the fluxes are going to be represented like this. And now we have everything. So we have the fluxes, we have the integrals here, volume integrals, this one, and this one is going to be 0 for this example, so I'm just going to neglect that. So the next step is substitute into integral equation. So it's going to be d delta x phi bar j over dt. This is the equation we had, plus fj plus 1/2 minus fj minus 1/2, which is gonna be approximated as d delta x phi bar j over delta t plus f hat j plus 1/2 minus f hat j minus 1/2. Which is gonna be equal to d delta x phi bar j over dt plus c phi bar j plus c phi bar j plus 1 over 2 minus c phi bar j minus 1 plus c phi bar j over 2 equals to 0. And why I could do this? Because this is the integral I had, right? The first term. Let's look at the first term. So the first term is phi j, right? So it's going to be phi jt. I'm just going to write it down here. Phi jt is going to be 1 over delta x and integral of that. So it's going to be 1 over delta x, the integral xj minus 1/2 xj plus 1/2 phi xt and dx. And we assumed here this is going to be phi bar j. So I can write this down as phi bar j is a constant value. So it's going to come out of this. So it's this whole thing is going to be delta x times phi bar j. And so the whole thing is going to be just phi bar j. Okay, so this is how I did this here. And then put this one here. Okay, so this is the first term, and then the other terms here come from these approximations. Okay, and so I want to further simplify this. So this is going to give me delta x d phi bar, because delta x is constant, d phi bar j over dt plus c. So these two terms are going to cancel out, this term and this term. It's going to be phi bar j plus 1 minus c phi bar j minus 1 over 2 equals to 0. Okay? And in vector form, of phi bar, and I show this like this, this is what we are going to have. This we will have d phi bar over dt plus c over 2 delta x bp, which is a matrix, minus 1, a tridiagonal matrix, 0, 1, phi bar equals to 0. So this is the final equation we have that we can solve with any software. Okay, so let me show it with this. And this is only if you do it with one component, and the other one is, this one is for the whole system. Okay, when you do it for vector, in vector form for the whole system, and this BP is a circulant tridiagonal matrix. Okay, so you can easily solve this. So we have first discretized this in space, and this is the discretization in space, and the only remaining step, which I'm going to show it as step 3, so the first thing was we did the grid generation. Step 2 was discretize in generic integral equation on series, or discretize in space, which we did here. And step 3 is solving this resultant linear algebraic system using time marching methods. So the only component is discretization in time and solving this linear algebraic system with those time marching methods that we talked about. For example, a simpler one could be a forward Euler method, or you can even use more complicated ones like Rangakuta and other ones. Okay, so you just need to integrate this in time, and then you will be able to solve this system. And then you will find the cell average values. So you will find these phi bars after solving this system. Okay. And you can even have some estimations for the fluxes at the boundaries, right? Because these are also shown with a second order approximation. You can say these are the fluxes at the boundaries once you find the cell average values. Okay, so this is the whole scheme of a simple example as to describe the whole scheme of finite volume, and this can be extended to more complicated problems with 3 dimensions, and also there are some other nuances like interpolations that I'm going to briefly mention. 2 important interpolation schemes for these finite volume methods next time, and this will be kind of an overview of finite volume methods. So to sum up, we solved this generic finite volume example in this lecture. Previous lectures we just had approximations of finite of surface integrals and volume integrals in terms of nodal values or cell average values. And in this lecture, I showed you a general example of 1D example. So the first step, as I said, was a grid generation step, and then we had to discretize this generic integral equation. So these were the discretizations for volume integrals that we showed here. And then this was for the flux term or surface integrals. And then this was the general discretized equation for most of the transport equations. And I considered a simple linear convection equation without any source and showed that for this example, so this is going to be the generic equation, discretized equation, and then you have to compute surface and volume integrals as functions of phi within the CV. So a simple first piecewise constant approximation is you assume the phi within that CV equals to the cell average value. This is a second order approximation that you can show it. And then the fluxes in terms of cell average values, we showed that there is a flux discontinuity, and second order approximation for that is to use these forms here for the left and right flux. And then we substitute this into the original equation. This was the final equation we obtained. And finally, we wrote it in the vector form. So in the vector form, this is going to be the system, the linear system that we want to solve. And then the next step would be to solve this using this time marching method that we discussed in the previous lectures. Okay, thank you very much, everyone.